Hello everybody. In this video we're going to continue the topic of fluid flow in Aspen Plus, and we're going to talk about the minor losses in Aspen Plus. However, I prefer to give this short video as a quick review on the minor losses so that we are aware of all the details that we will need to know while working on Aspen Plus, so that we don't waste time while working on Aspen Plus on discussing all the details that we're gonna put or input to the software. Just to revise the topic, we know that the modified Bernoulli equation takes this shape. We have the pressure, the velocity, the elevation in the 2 points, and this is the pump, that's the head generated by the pump, and this is the losses. And we saw in the previous videos that we can calculate the losses by getting the friction factor from the Moody diagram or from the equation, and substitute in the losses equation, which was F L over D V square over 2G. However, this is not the only source of losses, and there are two main sources of losses. The first one is the one that we just mentioned, which is due to the viscous flow of the fluid and the friction with the pipe walls, and this is called the major losses. And there are other losses that are or take place due to the presence of something that leads to the losses, either the change in the diameter or the area of the flow, or the non-uniformity of the flow, or something that is put in the pipe to change the direction or to regulate the flow. And whatever the cause of this, these are called the minor losses, just to differentiate between this and the major losses. And it's important to mention that having this named as minor losses does not mean that its value is smaller than the value of the major losses. We call it major because this is the type of losses that's gonna be there in all the pipes, in all the pipe flow. Because you will always have friction between the fluid and the walls of the pipe. But in many cases, you will have just a pipe without any minor losses, without any change in direction or change in the area of the flow and all these stuff. And that's why this is not always there, and that's why you call it a minor losses. So what can cause the minor losses? There are many sources of the losses. The first is the valves. And as you see here, the valve does change in the direction of the flow, and there is a constriction here, and that's why there are many, or a lot of loss is generated due to the flow in a valve. There are sources of losses, which are the entrance flow and the exit flow. And there is losses due to the fittings, and there are losses due to the sudden or the expansion and contraction in general. It's just the sudden expansion and contraction. In the next slides, I'll talk briefly about each one of them, just to have an idea why this caused the losses. So there are many types of valves. There are valves that are we call the shuttle valves, or whose function is to open and close the flow. The second is the control valve, which is used to regulate the flow. It allows half the flow, 3/4 of the flow, 60-70% of the flow to flow, and this is controllable. And there are non-return or check valves, and they are designed to prevent the backflow. We will see some types of all of each type of them. So for the shuttle valves, we see there is a gate valve. You revolve the handle and or rotate the handle, and as you rotate the handle, this shaft goes up and down, and it can totally close the flow or open it. There is the plug and ball valve. The handle rotates by 90 degrees or quarter turn, and by doing this opening will be either parallel to the flow, so the flow will pass through this opening, or be perpendicular, so the flow will be closed. There are control valves. This is called the most famous type of control valve is the globe valve, and as you see in the globe valve, the flow goes down and then up through this surface area between the valve plug and the and this area, and then it goes out from the other side. And again, you have this shaft. It's connected to a disc, and as you rotate the disc, this shaft goes up and down according to the percent opening that you want to open or let the flow pass through. There is the diaphragm pump. It's very close to this, but we have here a diaphragm to prevent the flow or the liquid from contacting the metal parts in case it's a corrosive material or something. And here you'd see there is the butterfly valve. It's like a disc, but it rotates whatever the angle that you specify, and by changing the angle you change the area of the flow, and this controls the amount of the flow going through the pipe. So as you see in all of them, there is a change in the direction of the flow, either going up and down, or by going in like an angle and then going back in the straight direction, or here by going down and up. And you'd see that in all of them you'll have constriction, and this constriction is a very important source of losses in the flow. The non-return valve or the check valve, it's a valve that allows the flow to go in one direction, so it's like a door. So if the flow goes this way, it's okay, the flow will go, and this door will not prevent the flow from going. And on the other side, if the flow goes this way, it is totally blocked. The second source of the minor losses is the entrance effect. And to understand what we mean by the entrance effect, it is, as you see, or as we know from the flow mechanics, this is how the velocity profile should look like. It's a parabolic profile here at the walls because of the no-slip boundary condition. This is zero velocity here and there. And as you go to the center, the velocity increases. And from this we can do our calculations for calculating the friction losses and all the pressure drop sources. But in the beginning of the flow, as like you have here a bigger pipe, or you have a lake or a big tank, and then the flow goes from this big thing or big reservoir to the pipe. The profile will not be as it is here. Here, what we call the fully developed flow, but here it's not fully developed. Still, there is the part in the center is not does not have this shape of the velocity, and that's called the developing flow. And the developing flow has higher losses than the losses that we get from the developed or fully developed flow. And that's why we have this entrance effect losses. And again, it's like the exit effect losses. If you have the flow coming out of the pipe going to like a big place, then you'll have the same effect on the other side. But this is gonna be flipped on the other side. It's gonna be starting from here and ending from here on the other side. Usually we do not do the calculations of the entrance effect losses due to two reasons. The first and the most important is that it can be neglected if the pipe length is more than 10 times the diameter. So for instance, I have a diameter of 1 inch, then I can and I have a length of 10 inches, then I can ignore, or more than 10 inches, I can ignore this entrance effect. And usually the ratio that we deal with is way higher than this 10 or the value of 10, and that's why we usually ignore it. The second reason is that we do not have clear or very solid way of calculating the losses due to the entrance effect. There are many ways of doing these calculations, but it's not as easy as doing the calculations for the other minor losses. That's why we do not usually do these calculations. For the next point is the expansion and contraction, and the expansion and contraction can be, or let's say what are the expansion contraction, what we mean by them. The expansion is the increase of the surface area from a small diameter to a larger diameter, like here and here. And the contraction is the change of the diameter of the flow from a big diameter into smaller diameter, like in this case and in this case. There are two cases for each one of them, which is the sudden and the gradual. So here you'd see that there is a gradual change in the area from the d small or the lowercase d to the uppercase d, and here is the same for the sudden for the oops, I think I did something wrong. This should go here and this should go here. I'm sorry, this is a mistake that I made. So I hope it's now right. Anyway, so you have we have this is contraction and this is expansion, this is sudden and this is gradual. Yeah, so this is right. So for the expansion and contraction, here we have a gradual change in the surface area, but here we have a sudden change in the surface area. And usually the losses are due to the areas that form at the corners here and the presence of dead zones, and the flow is not uniform at this part. And this generates a lot of losses. Of course, in this case, the losses are not as much as in the sudden contraction and expansion, and that's why we will see in the calculations later how the values will change for the losses. So in Bernoulli equation, we have the losses are calculated as a function of v squared over 2g, and we multiply v squared over 2g by kl, which is the just a factor that takes in consideration the losses due to the different types or any type of losses that we just talked about. And it depends on the type of minor losses, and it can be calculated either using formulas or from tabulated data or from graphs, as we will see in the next slides. So here, this is one. I didn't talk about this while talking about the sources of losses, which is the fittings. The fitting is the connection between two pipes, it's mainly between two pipes, and this is used to either change the direction of the flow, like here and here, with different angles, 90 degrees, 45, 180 degrees, or to split the flow, like in this case we have a T. The flow will go into outlets instead of one outlet. So we'll see for all these cases, or for each one of these cases, we will have a different value of K according to the type of the fitting that we're using. So you have an elbow here, it's 90 degrees. We'll have values for long radius, it's another specification of them. And for the 45 degrees, we'll have another value. For the 180 degrees, we'll have these values. For the T's, we'll have two options for the T, either to be a line flow, which means that the flow is going in this direction and getting out of the same straight line, the same flow direction. But if it's a branched flow, then the flow is going from this side and coming out of this side. And of course, this is more difficult or will generate more pressure drop due to the change in the flow direction. We'll have here a union, which is just a connection between two pipes. Here we see the valves, the globe valve. The value is very big for the globe valve because of the, as we mentioned, the big change in direction in the flow. We'll have a gate valve that is fully open or quarter closed, half closed, or 3/4 closed. And as the percentage of closure increases, the K increases, of course, because this lets a small amount of the flow goes, which means that the losses will be higher. Here we have the swing check valve. This is for the forward flow, it's 2. For the backward flow, it's infinity, because in the case of backward flow, as we mentioned before, it's gonna stop the flow totally. And the same for the ball valves and the other types of valves. So it's kind of something easy to do, is just to go to the table, search for what you're dealing with, and then just put the value of K that corresponds to it. For sudden expansion or for expansion and contraction, you would see here there is an equation or a graph that you can use based on the ratios between the two diameters to the power of 2. And you go to find the d over d power 2 and then find the k. There is like this table in the bottom for the gradual expansion and contraction, which is based on the velocity of the flow. And here it tells you based on the angle, which is this angle between these two or between the gradual increasing area part. You can find the value of k based on the d over d, and here for the contraction you would find the values of k for different angles. Of course, you will find in literature a lot of tables and data and graphs for different types of losses. I'm just showing these for the sake of demonstration, just to have an idea how we do the extraction of the KL data. One last thing here is how we connect the types or the pipe. There are two common ways of doing the connections. The first is what we call the flanged connections, and the flange connection is having a pipe with this flange, which is kind of disc which is welded to the end of the pipe, and it has openings for putting bolts or for connecting with bolts and nuts. And this is what we see here in this section. This is the pipe, and this is the flange, and this is the other flange. They are connected together, and of course there is a sealing or something like a gasket to prevent the leakage, and they are screwed to make sure that the connection is secure and there are no leakage. The other is the threaded connections, and as we see, this is how it looks like. It's doing threading to the whatever the pipe, the tube, or the connection, the valve, whatever thing that we're using. And they are two types, a male and female, and they get connected by rotating. You just connect this and then rotate them like the cap of the bottle, and it works. Of course, we use something like Teflon tape or some other of sealing materials to prevent the leakage in this case. Usually the threaded connections are used for small diameters. You can find this in the plumbing for homes and for like the kitchens and bathrooms. It's also used in the connections for lab equipment like gas chromatography and the pipes and or I mean the gas cylinders. The connections out of the gas cylinders, the regulators, and all these stuff are connected with the threading, because in this case the flanges are not going to be feasible, are not going to be easy to deal with. However, these are used for big diameters. It's if you go to industry and or any chemical plant, you'll find all the connections taking this shape. No threading is used there, to the best of my knowledge. I haven't seen it before. So this is important because in here, for instance, you see that the K's are there are two values of K for the same connection, but one is for flanged and one for threaded. And of course the threaded will be higher, because in case of thread we can just take another look. This part will have kind of a change in the area. There's usually the area is not here the same in both when you do it. Of course it should be the same, but there kind of change in area that takes place here, which results in high source of or results in high pressure losses. And this is what we'll see here for all the flanged and the threaded connections. You'd see that the threaded is higher, is much higher than the flanged. So the modified Bernoulli equation now will take the shape, or will not change actually. The original equation is going to be the same, but the difference will be in the definition of the H losses. Either or before we used just the major, but here we will put the major and the minor, and here is the HL major. It's this the equation, and the HL minor is KL V square over 2G. In case we have more than one source of minor losses, for instance, we have entrance effect, we have connections, we have valve, then we will add all the values of the KLs so that we account for all of them and multiply the sigma KL by the V square over 2G. So this is kind of the main point that I'm interested in covering in this video, and these are the points that we're going to use in the next video, inshallah, when we talk about the minor losses in Aspen Plus. So I hope it helps, and I'll see you in the next video, inshallah. Goodbye.